Hello again and welcome to another physics class. Today we'll be looking at electromagnetism. Under electromagnetism, we'll be explaining what electromagnetism is. We'll look at the uses of electromagnets. We'll look at the right-hand grip rule for straight conductors and solenoids. And then we'll look at steps to take to increase the strength of magnetic field around a straight conductor or around a solenoid. And then we'll wrap up the class by looking at how to calculate magnetic force on conductors that move in an electric field. So let's get started. First, what is electromagnetism and where is this idea coming from? Now, when a current flows through a wire, we know that there's a magnetic field created around that wire. Or, well, maybe we didn't know, but now I'm telling us that if you have a conductor and the conductor has charges flowing through it, that means there's a current flowing through that conductor. Because of that current that is flowing, there is a magnetic field created around that conductor. Moving charges, when charges move, which is what current is, when charges move, they create a magnetic field around the conductor in which the charges move. Now, this phenomenon is what is called electromagnetism. Now, this magnetic field that they create is not one that you feel. You don't usually feel it because it is very weak. It is weak and it has a circular shape. So, let's take note again that when you have a conductor that current flows through it, the flow of that current, the moving charges constituting that current, result in a magnetic field around that conductor. But then, how do we know the direction of the magnetic field around the conductor? There is a rule called the right-hand grip rule. Right hand. Meaning that if you want to practice this, you have to use your right hand. So what I'm going to ask you to do, wherever you are, is to pick up a pen, maybe your biro or your pencil, or you're using to jot now. Pick it up and hold it. Hold it such that you grab it with your arms, but your thumb is pointing upwards. Let your thumb point upwards towards the tip of the pen, while your other fingers curl around the pen. Now, if that thumb that points upwards, if it is pointing in the direction in which the current is flowing, meaning that if in your pen, let's say your pen was a conductor, and current was flowing from the bottom to the top, your thumb is pointing towards the top, meaning that your thumb is pointing towards the direction of the current flow. Now, the other fingers that are curled around that pen, those other fingers are curled in the direction of the magnetic field around that conductor. Your pen being a conductor now. So, if your thumb points in the direction, your right thumb, by the way, your right thumb points in the direction of the current flowing through a straight conductor, the other fingers will curl in the direction of the magnetic field around that conductor. That essentially is what the right-hand grip rule is. Now, this same rule is applicable for solenoids. What are solenoids? Solenoids are just like your coil, your straight conductor, but rather than making that conductor straight, you now coil it. You turn it into coils of wire. You turn it round and round and round and round and round until it makes a coil. What you have then is a solenoid. So when you have a current flowing through a solenoid, if your thumb points in the direction of the north pole of a solenoid, which is a solenoid is an electromagnet. We already looked at that in a previous lesson. You may want to refer to my YouTube channel and look for the topic magnets and magnetic fields. You will see what solenoids are essentially there. But if your thumb points in the direction of the north pole of the solenoid, the other fingers will point in the direction of the magnetic field in direction of the current around the solenoid. That is the difference between the right hand grip rule for straight conductors and that for solenoids. Now let's look at how we can increase that magnetic field strength around the straight conductor. Remember I said that the magnetic field strength is usually weak around the straight conductor, so we don't usually feel it. But let's say we now want to make it stronger. What do? All we need to do is to increase the current that is flowing in that wire. Increase the current flowing through your pen, using the pen example that we just did earlier. How do we do that? You connect your pen to a power source that has a higher voltage. That's a simple way to do it. So if you are using maybe a 3-volt battery before, and then you want a stronger magnetic field, then you can connect to a 12-volt battery. That will give you more current, and that will give you more magnetic field strength around the straight conductor. Another thing that we can do is to wrap the wire into a coil or a solenoid. As I said, you wrap that wire into a coil. A solenoid is just a long coiled wire. Now the shape of the magnetic field around the solenoid is the same as that around the bar magnet. As I said earlier again, look at the lesson Magnets and Magnetism on my YouTube channel. You will find what the magnetic field around the bar magnet is. Now, position of the poles can be determined using the right hand grip rule for poles. If the direction of the current is reversed, then you also reverse the direction of the poles. So if your current was curved in a clockwise direction before, and then your thumb pointed in the in the direction of the north pole of the magnet. If you now reverse your current to anti-clockwise, then you will have your north pole on the other side of that solenoid. Around the solenoid, we can increase the magnetic field by creating more current through the solenoid as well. That means connecting the solenoid to a higher voltage. Then you will have more current flowing through it. When the current increases, the magnetic field around that solenoid will increase. Another thing you can do is to increase the number of turns on the solenoid. So if you only wrap this 10 times, you may want to increase the number of turns by wrapping it 20 times. Then you have a stronger magnetic field around it. And the last thing you could do is to wrap that solenoid around a soft iron core. A soft iron core is like an iron material, a rod that is made of soft iron. If you wrap a wire around it, around that iron core, and you connect that wire to a power source, current will flow through that solenoid. As the current flows through that solenoid, the wire that is in contact with that rod will also get magnetized. That will now add to the magnetic field around the solenoid that you are creating. So we can wrap the solenoid around a soft iron core. The combination of two magnetic fields of the solenoid itself and of the soft iron core will give you a stronger magnetic field. A soft iron core and the solenoid together is referred to as an electromagnet. And what are electromagnets used for? The very common use that we'll find around is that it is used in heavy car dump sites, those sites where cars are dumped after they have served out their purpose with their owners, and then the cars are broken into their component parts. Now, large electromagnets are used to lift up those heavy pieces of iron in such scrap yards. Also, electromagnets are used in creating magnetic fields that are needed in generators and DC motors. Generators and motors are compositions of another topic that I have looked at, which you will also see on this YouTube channel. Another use for electromagnets is in separating mixtures. This finds application in dump sites. That's a very good example. In dump sites, where all sorts of waste are dumped, metals, plastics, and different kinds. If you want to separate the iron from the others, you just need an electromagnet to pick up the iron and separate the iron waste from the rest. And then also they are used in construction of regular everyday devices like the electric bell, the relay switches, the circuit breakers, and your telephone earpiece. Each of these will be looked at also in another lesson. Now let's look at magnetic force on a current carrying conductor. Now, remember we already said that a conductor that has current flowing through it has a magnetic field around it. We already said that. So when you have a conductor that is just by itself, but current is flowing through it, then there is a magnetic field around that conductor. Now, if you now place that conductor into the magnetic field of maybe another magnet. So now we have two things now that have magnetic field. There is a magnetic field due to the conductor, due to the current flowing in the conductor, and there's also the magnetic field of the magnet itself. So when you bring the conductor to the magnet, to the field of the magnet, you have two magnetic fields that are now interacting. So this interaction between these two magnetic fields will lead to a force being experienced by the conductor. Now, that force that the conductor experiences is because these two magnetic fields that are now interacting to each other will begin to exert some kind of force on that conductor, begin to kind of maybe push or pull or cause that conductor to move in one way or the other. Now, how to find that force is just by multiplying the magnetic field strength, which is what B stands for, by the current flowing through the conductor and the length of the conductor, and then by the sine of the angle at which the conductor is placed in the magnetic field of the magnet. So, if you have your conductor placed in a magnetic field at, say, angle 20 degrees, your theta there will be 20 degrees. If the angle between the magnetic field of the magnet and the conductor is maybe 90 degrees, then your theta there will be 90 degrees. Now, let's see an example. They are asked to find the magnetic force on a conductor of length 65 centimeters. The current is given, and then you are also given the magnetic field strength, 10 Tesla, and 3 different angles. Now, the solution for the first one, the angle is 60 degrees. As I said, F equals BIL sine theta. Don't forget, your length must be in meters. Whenever you are doing calculations in physics, make sure the quantities and parameters you are using are in SI units. Your length must be in meters, not in centimeters. You cannot get a force which is measured in newtons when you have used a length which is in centimeters. The length must be in the SI unit as well. So doing that, you have 10 times 10 times 0.65. 0.65 is from your conversion of 65 centimeters to meters. And then sine 60 degrees, because the angle between the conductor and the magnetic field of the magnet is 60 degrees. When you multiply that, you get 56.29 newtons. Still on the previous question, the second part is that the angle between the conductor and the magnetic field is 90 degrees, meaning that both the field of the conductor and the field of the magnet are perpendicular to each other. Now, 90 degree, sine 90 degree is 1. So you just do 10 times 10 times 0.65 times 1, and you get 65 newtons. Now, if you look at when the conductor and the magnetic field are parallel to each other, when they are parallel to each other, there will be no force exerted. Why? Because the angle between two things that are parallel is 0. Many students believe that the angle between two lines that are parallel is 90 degrees. No. Angle between two lines that are not meeting, the angle between them is not 180 degrees. It is not 90 degrees, it is 0 degrees. You cannot have an angle between two things that don't touch. So, if your theta is 0, then sine theta will also be 0, and everything multiplied by 0 will give you 0. So, this will essentially tell you that if your conductor does not make any angle at all, that means if it's parallel with the magnetic field, there cannot be a force on that conductor. On the other hand, the highest force that a conductor can experience is when the conductor is perpendicular to the magnetic field, because that is when you will have the your sine 90 to be equal to 1. That's the highest possible value of sine of angles that you could possibly have. So let us take note of that. Now, you remember that we already said that charges constitute current. Moving charges constitute current. So essentially, when we talk of current, what we are really saying is that some charges are moving, not static, not just charges being there. The charges are moving. So if we do not want to talk of current as a quantity itself, we can talk of the charges that are moving as a quantity. That one too can be used to find the force on a conductor in a magnetic field. So if charges are moving, like every moving object, what that means is that they have a velocity. Moving charges, like every other moving object, like a moving ball, has a velocity. So if they have a velocity, then the formula for F in this case is QVB sine theta, where Q is the quantity of charge, which is measured in coulombs. V is the velocity of the charge, which is measured in meters per second. B is the magnetic field strength or flux density in Tesla. And then, of course, your theta is the angle between the charge and the magnetic field. So invariably, we are saying that you can use formula F equals BIL sine theta, as well as formula F equals QVB sine theta to find the magnetic force on a conductor in a magnetic field, depending on what the parameters we are considering are. Let's look at another example with respect to moving charges in a magnetic field. As we said, the formula is F equals QVB sine theta. So you are given the charges, you are given the velocity of the charge, and you are given the magnetic field strength, you are given the different angles, and you are asked to find the force. I would advise that you try to take down this question and solve it by yourself, even though the solution has already been provided. I will advise that for you to be able to get a hang on this topic, you solve this topic by yourself. Q is a charge, which in the question is an electron of charge 1.6 times 10 to the power minus 19 coulombs. V is the velocity, which in the question is 5 times 10 raised to the power 7 meters per second. And B is the magnetic field strength, which is 8 Tesla. Now you solve individually for at perpendicular, when your charge is perpendicular to the field, or at 30 degrees and then parallel. For at parallel, I don't have to say again that by now you know that if two things do not meet, if they are parallel, the angle between them is 0. So straight off, the force you will get for that one is 0 newtons. As I said, this is the last part of the solved example. Now you have some assignments that I have also carefully chosen so that you can try your hands on this topic. So I will advise that you attempt this assignment. And if you still have any comments or you want to ask a question, please feel free to drop a comment and I will reply. Thank you very much for today's lesson. I believe this has been helpful. Hope to see you in another lesson.